talk about SDN. We say that in traditional networks, we have some routers. In a router, we have a flow table, we have a forwarding table or routing table, or flow table or something like that. This table, this forwarding table, shows us the passes for the packets. The router receives some packets, and then it uses the forwarding table to determine the forwarding path of the packet according to the destination IP address of the router. Okay, and inside the router, according to the fields in the header of IP header of an IP packet, we can make some decisions in traffic engineering and something like that. For example, we can check the header of packets and apply quality of service process. For example, modifying a packet or dropping a packet, marking a packet, and doing something like that. So in layer 3, we have to do forwarding, and also we have some other tasks to do, checking the header fields and applying some possible actions on the header of those packets. And all of these actions will happen just in the layer 3 of the network. Okay, here we can have a flow table instead of a forwarding table in layer 3. But what is a flow label? In the network, we have a phrase flow, word flow. But what is a flow? A flow is a bunch of packets who are sending from similar sources toward a similar destination, or a bunch of packets with similar paths. So I define the flow as a bunch of packets who have similar routes, similar paths toward their destinations. So I can group them, and I know that according to this definition, I know that I can apply similar tasks, similar process on those packets, because they are similar. So I should act in a similar manner with all of those packets. Okay, so I can use this definition flow, to make decision A path. Path means a route. Path. Shared path. All of the links in the network are shared because we are using internet, and we know that the internet uses uses packet forwarding, uses datagram structure, datagram switching structure. Okay, instead of secret switching, we use packet switching strategy. So the passes, all of the routes in the network are shared. Okay, but among those shared passes, we have some special traffics with similar passes between source and destination. I can apply similar methods, or I can do everything. I can I can do similar process on those packets, and now and I call them as a flow. So instead of thinking instead of looking on traffics as separated separated packets, I can look on traffic as separated flows. Just I should learn about those flows and apply similar strategies on them. So the only thing that I need is a flow ID. We know that in header of IP packet version 6, IP version 6, version, excuse me, version 6, in IP version 6, we know that we have a flow ID field. Okay, just we can define that field in the routers in the path. Okay, in the path from source and destination, I can define those flow labels, those flow IDs, and then I'm writing that flow ID in the header of IP packets. So when a packet arrives to an IPv6 router, instead of checking the destination IP address, the router can check just the flow ID or the flow label of the packet. The flow label in IP version 6 has 24 bits, but the IP address version 6 has 128 bits. So it's much easier using those flow IDs is much easier than using IP version 6 addresses. So we can create a table similar to the forwarding table. We called it as a flow table. Okay, create this flow table, and in this table we just write those IP labels, those flow labels, and then in the next field we can simply write, okay, the IP for the packets belongs to IP, belongs to flow ID X, for example. Do something like it. For example, something like this. For example, send those packets via output B, output number B, okay, or mark those packets, or applying other strategy, I don't know, or even applying priority or count those packets or doing something like that. So we can use a flow table. We use the flow table instead of the forwarding table to match the values in the header of the packets and doing something with packets, for example, dropping it, forwarding it, modifying it, I don't know, applying some priorities on the packets, or counting number of bytes or bits or something like that, or number of packets, something like that. Okay. Look at this one. For example, here, this router has 4 different routes, 4 different interfaces, and in the flow table you can see, for example, if the source is not important source address, but destination is 3.4 point star star, means something blah blah. The rest of this packet is not important. A packet with something like this elements or properties should forward via interface number 2, or a packet with source address of 1.2 point star with destination star point star point star point star should be dropped, or the source address 10.1.2.3 with destination address of stars should send to a controller. Look at this. We define a flow as a bunch of packets, a group of packets who has similar source addresses and destination addresses. Similar source and destination address. Okay. It means that the source address of all of those packets are similar together, and their destination are similar together too. So we can use this strategy for routing packets efficiently, more efficient than the traditional structure. In SDN, we use protocol OpenFlow. It's dominated in SDN. Okay. In OpenFlow, we use flow table. Each record in a flow table has 3 separated parts. The first part is match part, then action, and finally status fields. You can see the information recorded in a flow table here. You can see those details here in this slide. I never ask you to keep this information in your mind. Okay, don't remember. It's not necessary to remember them. But look at this one. To define a flow for matching, we are using information in layer 2 and layer 3 and layer 4. So to define a flow, I'm using a combination of this information. For example, source MAC address, destination MAC address, Ethernet type, VLAN ID, VLAN priority, IP source, destination IP address, IP protocol, IP pass bit, TCP source port, and TCP or UDP destination port. I'm using all of this information to define or to find a flow. But maybe someone asks me, okay, you are talking about flow ID, but what is this? Here I cannot see flow ID. Flow ID. Where is it? Please. Here I'm using this information with IP version 4. I have flow label or flow ID in IP version 6, not version 4. So in IP version 6, I can make it simpler than this. Use just a flow ID. But in IP version 4, I have not a flow label. So I have to store all of those information. This information can help me to determine different flows in a network. In action, you can see that the action can be forwarding or dropping or modifying or encapsulating and forwarding toward the controller. And status information are something like number of packets and number of bytes of those packets. There are some counter information here. Here you can see, for example, different examples of records of a flow table. For example, you can see here we are only care about the IP destination. If the IP destination address is 51.6.0.8, the packet should send through port number 6. Look at this example. Just I determine one field, not the whole of those fields. It's very important. In a flow, just in this flow, just I'm care about the destination IP address. As another example, in a firewall, I can say that if the destination port number is 22nd, those packets should be dropped. It's a firewall strategy. Or if the source IP address is 128.119.1.1, again, the packet should be dropped. Okay? So I can use information simply to determine what should I do with different packets. Or here, I'm determining a flow using its destination MAC address. send frames with destination MAC address of 22.87.23.11E102. Those frames should be sent over port number 3. So I can use information in the flow table easily. I can use them easily to do what should I do. Okay. So here I can see that I can use the strategy in OpenFlow for in different task and process in a network. I can use this structure inside a router to find a match between those addresses with the real destination. In a switch, I can use MAC addresses. In a firewall, I can match different port numbers, or in a NAT, I can replace IP addresses with a new one, or I can rewrite IP addresses in the header. Okay. But what OpenFlow does is that I'm using a controller, an OpenFlow controller. This controller gathers the information inside the whole of network, whole of information of all of networks, okay, whole element in the network, and then it creates the flow table. Flow table for the whole network. Again, creating the flow table for the whole network. It means that here, this in this figure, this OpenFlow controller creating a flow table, creating and managing the flow table in S3, S2, and S1 routers. It means that those routers, those 3 routers, just do and act based on the information prepared by the OpenFlow controller. Those routers never think about the passes. They don't worry about controlling mechanism in the network. They never run routing algorithm or think about the strategies. They never do that. Just simply they receive the information. They receive the information and from the controller, OpenFlow controller, okay, just they receive from the information from the OpenFlow controller and act based on those information. They just update the flow tables based on those information and then act based on that. So this controller determines the passes inside the network. For example, this controller says, okay, host H6, for example, should send its his information from in the past from S3 to S1 and then S2, for example, to H4, or from S2 to H3. And at the same time, H5 should send its packet through S3, S1, and then S2 toward H3. Okay, these routes are determined by the open flow controller. The controller decide and manages all of systems in the network. So by this strategy, I can apply different policies in my network centrally. Why? Because the controller make decision about the whole network. So I can apply my, for example, security strategy in the controller about different traffics in my network. Look at this one. Example, the S3 learns that it should do something like this. The S1 learns the information in its flow table, and S2 again learns about the flows around itself. Okay, and again I should repeat that these information are prepared by the controller, by the open flow controller. This router never run routing algorithms by themselves. They just receive the results from the open flow controller. Okay, so in an SDN strategy or in open flow structure, I'm making decision in the controller, and then I advertise those information to different routers and systems in the network, and they should just find a match and take action. Local actions. Those actions are locally inside a router, inside a switch, inside a firewall. But who determines them? The controller inside the network. So simply I can see a network programmability in this strategy. The programmer can apply his strategy for network processing inside the controller, and then using that controller I can apply those strategies in different systems in the network. And using this strategy, we can see that this strategy can help us more generalized programming capabilities inside a network. Okay. Okay. Next section of the last section of this chapter is middle boxes. But what is middle box in a network? According to RFC 3234, I can say that any intermediary box performing functions apart from normal standard functions of an IP router on the data path between a source host and a destination host. In a simpler form, meat boxes are those network process along the path of network. We have several services, several network services in the networks. For example, we talked about NAT. We know that NAT is one of the fundamental services inside a network. For example, firewall IDS. They are security tools, security process. We have load balancer. They shape the volumes of traffic in my network. We have network caches. It's very important for us to use those caches because they help us to reduce the network delays along the paths. We have several specific applications inside the network. For example, CDN or content distribution networks. We can distribute different information between different networks. For example, let's suppose that I have a TV network. Okay, a TV inside Iran. Okay, if I send information from a central server, it would be congested. Why? Because it's one server. Instead of that, I can define different servers in different regions inside the Iran, in different cities in Iran, and then I can replicate the information from my primary server into the other servers in my network. And then when someone asks me to get a service from my server, I can redirect his request to the nearest server, to him, to the user. Okay, it's content distribution network, or CDN. So in today's network, we have lots of middle boxes in our networks. Most of them are using hardware solutions, but we are moving toward using or presenting different APIs to handle or to create an access to those hardware implementations or programming actions. Okay, we are using this as a white box hardware, using this programming capabilities. And now we have two new elements in our networks. The first one is SDN, or software defined networking. We talked about SDN and we said, okay, we have a central controller inside the network, and that network would manage all of my network. My private network, my public network, I don't know. It's not important. That central controller can manage the whole network. It can control, it can configure, and can manage my whole network. But there is another important strategy too. We called it network functions virtualization, or NFV. NFV is titled with SDN. If you read or follow the papers in computer networking area, you can see mostly SDN and NFV are tied together. They come together. Okay. In NFV, we try to virtualize the server of network functions or the server of network process. Virtualize all of them. For example, instead of having physical routers, I can prepare virtual routers or virtual firewalls or virtual gateways or something like that. Same as computers. Okay, in today's computer networks or applications, we can see there are several virtual machines are created and are managed in data centers in different organizations. You have several isolated virtual machines. Okay, and you can see the benefits of those separated machines. Instead of using a physical machine to handle the whole services, I can present several virtual machines, and then in those virtual machines I can define those process separatedly. Okay, and use the benefits of virtualization in my network. Okay, and even in cloud, the base of a cloud platform is using virtualization. Okay, and now in computer networks we can use virtualization too for different functions in network. I can prepare a server inside my computer, and in that server I can have a virtual system, a virtual server for DHCP service, a virtual server for DNS service, a virtual server for NAT service, a virtual server for multicasting, and several other functions. I can prepare different virtualized machines inside a computer. We call this as network functions virtualization. It's the future of all current networks. And again, similar to SDN, again here we have white box hardwares, programmable services over the networks. Okay, let me to again to watch the TCP/IP protocol stacks. If I look on TCP/IP protocol stack, I can see this stack has 5 different layers. Each of those layers has its own protocols. In the first assignment, I asked you to name those protocols in different layers. For example, you could say, okay, in the layer 2, I can see, for example, Ethernet protocols, point-to-point protocols, Wi-Fi, Bluetooth, or something like that. In layer 3, we have IP protocol. In layer 4, we have TCP or UDP protocols. And for example, in layer 4, I have HTTP, SMTP, RTP, and other protocols. Okay, but it's very interesting that among these protocol stack, in the middle of these layers, in layer 3, we only use IP protocol. The only layer with only one main protocols. In the rest of those layers, you can see a bunch of different protocols, several protocols. Even in layer 4, we have 2 different protocols. Okay, but in layer 3, whole packet should be sent over IP protocols. They should cross the IP protocols to move toward the networks. Okay, this is why the IP protocols became dominant in today's internet. One layer, one protocol, and the whole systems inside the internet should adopt themselves with this protocol. So it's better for them to implement this protocol inside themselves. Okay, so I can simulate the TCP/IP stack as a glass, as a hourglass, something like this. But when we look in details of layer 3, we can see there are several other protocols are placed in this layer. For example, when I'm talking about NAT protocol, it's in layer 3. When I'm talking about firewall, it's on layer 3. When I'm talking about caching in a network, mostly it's on layer 3. When I'm talking about NFV, it's on layer 3. So there are several other protocols who are in the layer 3. And now I know that those protocols using, for example, NFV, I can get access to those protocols. I have, they give me programming handles. Okay, so when we talk about internet, the architectural principle of the internet is this: the goal is connectivity. The tool is internet protocols, internet protocol or IP. And the intelligence is end-to-end rather than hiding in the network. You can read IFC 1958. What does it say? It says that an internet should present a simple connectivity structure using IP protocol. And this protocol should hide the whole complexity of network to me, should hide all of those complexity from me. It should be intelligence. And why IP protocol is simple? Because it tries to move the complexities to the edge of networks, the network edges. It tries to make it simple, a simple core. If I try to compare it with the circuit switching strategy, in circuit switching strategy, we have a reverse conditions. In circuit switching, the edge of networks are simpler, but the core of networks are very complex. But in IP, I say that, okay, edges are complex, but the core is simple. And I can say that it's a trump card of IP. Why IP protocol conquers the whole networks in the world. This is the reason. It's simple. I want to send the traffic. I want to connect to internet. It's my hardware responsibility to handle the problems with this connection. It's my network, my access network responsibility to handle the complexity. It's not the problem with the core of the internet. It's my problem, my network problem. It's very important. For example, in traditional public telephone, if you remember, or if you have information about the public telephones, you can see that. For example, if I want to add one phone line to my my telephone center, I should prepare several hardwares to do that, or I should have enough capacity to do that. But in computer networks, in internet, we never think about it. Just I'm connecting to internet when I need. It's very simple. Just when I need. Wherever, whenever. It's not important. My network, my computer, my network should handle the connections. It's not the responsibility of core of internet. Okay? And now you can see in several protocols in IP, TCP/IP protocol stack, most of network functionalities are working end to end. For example, if I'm excuse me, wait a minute, please. for the interrupt. Uh, for example, I'm talking with you using this platform, using Adobe Connect platform, okay? In this service, I need a reliable data transfer. I need a service for I need a service to handle congestions in the network. But I know that this Adobe Connect service or process just works on my computer. I'm an end user. I'm an end user here in this network. So I have not enough authority to work with the network. So what should I do? How can I transfer the data reliable? How? It's very important. Sometimes I can use some protocols inside the network to prepare some reliability in sending traffics. For example, when I'm sending one packet from one system to its neighbor, hop by hop, I'm using layer 2 protocols or MAC protocols. In MAC protocols, the MAC protocols prepare reliable data transfer for me. When I'm thinking about reliable data transfer, hop by hop. Okay, should I rely on that protocol in layer 2? Maybe yes. For some applications, maybe yes, but not for the all applications. Some applications needs more reliable data transfer. So in those applications, I can use, for example, layer 4 data transfer protocols. For example, if I need extra reliability for data transferring, I can use TCP protocols in layer 4. If I need extra reliability for data transfer. If the reliability prepares in layer 2 is enough, I can use UDP protocols in layer 4. But if I need extra reliability, I can use TCP protocols in layer 4. For example, if I need congestion control strategies, I can use TCP protocols. It's an end-to-end protocol in layer 4. But my network also has several tools, several processes, several strategies to handle congestion inside the network by itself. So what can I see? I can see that we have several protocols inside the network. Different protocols with different responsibilities and different activities. If they are enough, I can use them easily. But if I need something more, I should prepare additional tools. I should use more tools. but it's not the responsibility of my network. My network does its best to transfer the data between the source and destination. Okay? In the past, I said the packet switching strategy uses the packet switching mechanism uses best effort strategy. It does its best. But if you need something else, if you need something more, it's not its responsibility. Okay, you can create, you can implement those extra requirements. You can implement those extra requirements end to end in your applications. So look at this one. This is, yes, Muhammad. This is the last slide of this chapter. I will finish it very soon. Okay? So, in the first of 20th century, we had used phone networks. In those phone networks, we were used dumb telephones, and the network is the core of network things for us. But in internet, we can see the end system things themselves, and the network, the core of network, does not, nor the core of network. Okay, but after 2005, we can see now that okay, the core of internet can think too. So our today's internet is an intelligence entity. The end system think they are intelligent when I'm comparing them with telephone systems. If you break a telephone, a traditional telephone, if you break it, if you open it, you can see there is nothing inside the phone. Okay, but if you open the door of a, for example, a cell phone, back end of a cell phone, okay, or if you open a door of a case of a computer, you can see there are several complicated circuits and boards inside the computer. Okay, so in internet we have smart tools and devices at the edge of networks, and the core is not intelligent, but using SDN, using NFV structures, we can see the core can be intelligent too. We can write programs, several other programs for the core of internet. So we are moving toward programmable network devices, programmable computer networks, intelligent networks, intelligent end systems. So we are moving toward a new age in the human lives. Okay? That is the end of chapter 4. Is there any question? Any question? Okay, again, I'm sorry for the today's problem, and thank you for joining the class. Have a good day and bye.